So, welcome back to the second lecture. In this class, we will see how to assemble the element stiffness matrix into a global stiffness matrix. So, we have discussed how to write for the local coordinate stiffness matrix, and how to transform it into the global coordinate by the rotation matrix. So, the global coordinate stiffness matrix will be the corresponding displacements in the element which is expressed in a global coordinate level. So if we have three members, the three member will have its own element coordinate. Okay, so we are by our matrix, rotation matrix, we are converting that to the single global coordinate displacements, and then we can just add the element 1, element 2 plus element 3, which are in the global coordinate, to get the total stiffness and the other values in the global coordinate level. To make it clear, we will see a problem. We will see a definition: assembling the global stiffness matrix for a plane truss. So previously we have deal only for the member 1, 2. We have found the element coordinates for that one, r for the r matrix for that one, and we found in a global level. So this will be the real case where there will be one element, two element, three element for this case, to the minimum number for making a truss with similar support conditions, and a force is applied here. Okay, so the local coordinates are expressed as, for the element 1, 2 left side, 3, 4 right side, and local coordinate for the second element will be 1, 2 on the left side, and 3, 4 on the right side. Similarly for the third element. So these are the action or displacement components in the local coordinate of the member. Okay, now we are dealing with the global coordinate. So in the case of global coordinate, all the coordinate will be purely vertical or horizontal. Okay. Even in the case of element coordinate, it will be aligned in the line of the element and perpendicular to the element. In the global, it will be always vertical as well as a horizontal to the plane of the paper or the plane considered. So we have 1, 2 for the left side, then other joint, second one 3, 4, and the third one 5, 6. So these are the joints where the global coordinates are drawn. These are the action or displacement components in the global coordinates of the structure. We'll just split this one. So 1, 2, 3, 4, then 3, 4, 5, 6, 5, 6, 1, 2. This means that the total deformations in 1, 2 will be the sum of the displacement for the element 1 here plus displacement of the element 3 here. So we should add this thing to get the global coordinate value. Similarly, the peak one 3, 4 will be the sum of this portion and this portion, and this portion in the main truss will be the sum of this one and this one. So you have to properly add it in the matrix to get the global stiffness values. Okay, so we are considering the member 1 first. So we have already derived the global stiffness matrix for the member 1. We have in the previous slides. This is for plane member. Yeah, this one. Slide number 13, we have discussed this one, which is the member stiffness matrix in the global coordinate for a plane truss member. That matrix is written here. It's written here, and this SM1, SM1. So this will be for the member 1 in the global coordinate. So the 1, 2, 3, and 4 are the global degrees of freedom. So you know, for the member 1, you have 1, 2, 3, and 4 as the global values. So it is correctly placed 1, 2, 3, 4. For the second member, this member, you have 3, 4, 5, and 6. So yeah, this will be for the member 1. Even it is a 6 by 6 matrix, we have 6 values, degrees of freedom. So this will be the total matrix, and the contribution of the first element will be the 4 by 4 matrix. This one, right? And for the second element, we know it is the 3, 4, 5, 6. Here also 3, 4, 5, 6. So aligning in that way. So 3, 4, 5, 6, 3, 4, 5, 6. So this will be the contribution of the second element to the global coordinate. Okay, now we can guess for the third one, which will be this one. It is 1, 2 as well as 4, 5, 6. 1, 2 as well as 5, 6. So you can write separately for this element first, then you can add into the matrix. So 1, 2, 5, 6 will be for the member 3. So look in the global stiffness matrix. Now you have different elements coming. Like see, for the first element you have a value here, and in the second matrix it is not there. But for third matrix you have a value there. So this one plus the previous value, it is the first element value, will give you the net value for this element, right? So should add accordingly to get the global assembled stiffness matrix for the truss structure, which is shown there. So this is the easiness of the direct stiffness method. As we're converting the individual element coordinate into a global coordinate, we can assemble in the global level. Hope it's very clear for you. So this is the basic, or this will be the method of doing for all the problems, even if for the plane frame, all the things should arrange it properly. Should first write for the individual elements, then you should add correctly so that it will be forming a global stiffness matrix. Then to solve, this will be the matrix F is equal to stiffness into U, and the should apply the boundary conditions to get the required value. So you have here U1. So this was the global one. So U1, then U2. Let's see the thing. That is yeah, this is enough. This is enough. This is the global one, right? So you have zero displacement here as it is at hinge. There is no displacement here, as well as there is no displacement here. So this will be the one U1, and here also you have zero displacement. So those things are written there. There is U1, U2, U5 and U6 is equal to 0. Okay, so in the global coordinate, we have 1, 2, 3, 4, 5, 6. So this value will be 0, U1, U2 0, as well as 5 and 6 will be 0. There will be some deflection in the top. Okay, so this will be the contribution of the member 1 to the global stiffness matrix. And assembling total, you'll get the complete global stiffness matrix for the truss. And applying the boundary conditions, as we discussed, U1 is equal to U2 is equal to U5 is equal to U6 is equal to 0, being the hinge conditions for the truss. Boundary conditions, you can cancel all these matrix which corresponds to U1, and only the U3 and U4 will be there. So only this will be remaining with the U3 and U4, because U1, U2, U5, U6 all are 0. And simplifying, you will get the reduced equation system after imposing the boundary conditions as F3, F4 is equal to SM1 33 plus SM2 11 plus then SM1 34 plus SM2 12, SM1 43 plus SM2 21 will give you U3, U4. So this reduced equation system can be solved to get the unknowns, because two unknowns are only there, and have the matrix to solve it. Then D local is can be found from D local is equal to RT into D global. This we have discussed in the last video. and for each member d local is equal to dmi, because it's doing in the local coordinate, and the member end actions AMI is equal to AMFI, which is the fixed end actions on the member, plus SMI into DMI. AMI is equal to AMFI, fixed end actions on member, plus member stiffness matrix into the displacement component of the member. So all the things are in the local coordinate. We also know that dmi is equal to, which is d local is equal to rt into d global. So we are taking from the starting between the member displacement and the global displacement. So applying the DMI here. So AMI is equal to AMFI plus SMI into RTI into D global I. So to recollect the Barrett's stiffness method procedure, the first step is to get the member stiffness matrix for all the members. So you should get the individual element stiffness matrix for all the individual members, then get the rotation matrix for all the members, then transform the member stiffness matrix from the local coordinate into the global coordinate, which is SMSI structure. And step 4, assemble the global stiffness matrix, what we have seen for the truss by clubbing different 1, 2, 3, 4, 5, 6. And for the step 5, apply the boundary condition to get the reduced stiffness matrix SJJ. Then there are some more procedure to find the member end actions. The step 6, find the equivalent joint load from the applied loads on each member. Then transform the member actions from local coordinate to the global coordinate to get the transformed load vector. Then find the combined load vector AC by adding the transformed load vector and the applied loads directly joints. So these things we have discussed in even the flexibility method, the equivalent joint load method. Right? Suppose if we have a beam where the load is exactly at the midpoint, so we should convert it into the fixed moment, and then we can add it with the actual loads to get the final combined load vector. Then the reduced load vector AJ by removing the members in the load vector corresponding to the boundary conditions. And in the step 10, get displacement components of the structure in global coordinate. dj is equal to sjj inverse into aj. As a step 11, get the displacement components of each member in the local coordinate. Is d local is equal to rt into d global, which is a known equation connecting the global displacement and the local displacement with the rotation matrix. Then get the member end action, which are disclosed AMI is equal to the fixed end moment plus the SMI into RTI into D global, and get the reactions AR is equal to minus ARC plus SRJ into DJ. where ARC represents the combined joint load, actual and equivalent applied directly to the supports. Let's see a problem. So this will be the general procedure of solving the problem by the direct stiffness method. In a nutshell, first you should write the element stiffness matrix, which is well known to you now. So element stiffness matrix has to be converted. Element stiffness matrix, which will be in the local coordinate, has to be converted to the global coordinate by the rotation matrix, and then you should apply the boundary conditions to get the displacements in the global coordinate. Then you can do the similar steps for the load also by the equivalent joint load method and by the combined joint load. Then you should can relate it and apply the boundary conditions solving the problem, and then it can come to the element level to get the element coordinates, the displacements at the various element coordinates. Okay, we'll see this problem. Problem number 1 with A, B, C as supporting here, A, B, C near to the board, and we have point O where 5 kN is acting. Consider AE as a unity. So unity value will be 1, and the total depth will be 1 meter, and the various angles are given 30 degree, 90 degree, 120 degree, all are given. The members will be the joints will be 1, 2, 3 and 4. So we have in this one mainly 3 member. Member 1 indicated in this square is 1. This is actually 2 and this is actually 3 members. This is actually the loading, so this is not a member. So for the member 1, connecting node 1 and 4, member 1 is this one, connecting the node 4 and the node 1, and member 2 between 2 and 4, and 3 between 3 and 4. Just the connectivity. Now you know the member stiffness matrix in the local coordinate. So the member stiffness matrix in the local coordinate without considering the restrained degree of freedom. For the member 1, the 1 and 2 are the restrained degrees of freedom. So we know for this member 1, the topmost point is actually tied to the support. So there is no movements at the 1. Only movement will be there at the O, which will be the 4th node. Okay, sir, there is no movement here for the support condition. Only should have the movement 3 and 4. Even the total matrix will be Sm is equal to EA by L 0 minus EA by 0 0 0 0 0 minus EA by L 0 EA by L 0 0 0 0 0. So you know the condition very well before that 1 and 2 will be 0. So this 1 2 1 2 1 2 will be 0. So this entire thing will be 0. But remaining is this EA by L 0 0 0 SM1. The local degrees of freedom of 3 and 4 is equal to EA by L. We know the EA value is 1, and the length of the corresponding member will be this is actually 1 meter. This is 120 degree. From the hypotenuse right angle theory, you can find the length of the member CO, which will be equal to 1.155. Similarly, for the member 2, we know that here also the 1 and 2 will be 0, being supported here, and also for the member 3 also this will be 0. So once you know the values well before, you don't want to make the matrix very complex, right? So it will be easy in assembling also. Otherwise, you should write all the matrix values in the corresponding points and making it into a big matrix, and then you have to cut it and solve this. So initially you can skip that ones, provided you know the support conditions well. Member 2, 1 and 2 are the restraint degrees of freedom, 1 and 2, 3 and 4. So the degrees of freedom will be only for the 3 and 4. It will be same as the previous one, A by L 0, 0, 0. So the values are written here. The length of this member is actually 1 meter from here to here. So that's why A by L is equal to 1 by 1. Similarly for the third one, here also the this will be the restraint degrees of freedom. So A by L 0, 0. So here the length will be 2 meter. From this 1 meter you can find that OA will be equal to 2 meter. Hence it is 1 by 2, 0, 0, 0. Then the rotation matrix RTI. So the equation is directly known to you, matrix is directly known to you, cos theta, sin theta, minus sin theta and cos theta, and applying the angle theta is equal to minus 60 degree because we have derived the equation based on a clockwise rotation. So sorry, anti-clockwise rotation because we have derived the thing like this one, right? Equation measurement in theta. So hence a clockwise moment will have a negative value. Theta is equal to minus 60 to give the 0.5 minus 0.866, 0.866 and 0.5. For the member 2 also will have the theta is equal to minus 90 degree to give the matrix 0, minus 1, 1, 0. For the member 3, theta is equal to minus 150 degree. With respect to this, it's actually a clockwise one, but downwards. Cos theta, sin theta, minus sin theta, cos theta will give you minus 0.866, minus 0.5, 0.5, minus 0.866. So now we know the SM1, SM2, SM3, which are the local coordinate stiffness, and we know the rotation matrix as RT1, RT2, RT3 for the individual elements. So the transformed member stiffness matrix or SM1 is equal to RT1 T SM1 into RTI. This is about the first element, and for the second element also you can find the SMS2, SMS3 also find for the third element. Then you can add for all. And in the global coordinate, we have at the point O, it will be 7, 8, 7 and 8 will be the global coordinate value. Instead of like for the global coordinate, this was initially 3, 4 for the first element, and it will vary 3, 4 for all the elements for in the local coordinate. And in the global coordinate, this value will be 7, 8. Hence, the values are correspondingly added because you know very well that only the deflection happens at the point of tip of this point O due to the member 1, member 2 and member 3. So you should have definitely just add it up to get the final matrix. So all the three values contributions from all the elements are added up to get the global degrees of freedom. This is the reduced global stiffness matrix since the restrained degrees of freedom were not considered. Hence, the boundary conditions are automatically incorporated. That means we already deducted, we are already cancelled that matrix. No, we reduced the matrix previously. So you don't need to cancel here after assembling all the values. Directly, this will be the reduced global stiffness matrix. Then the loads Aj is equal to 0 and minus 5 at the point 7. Point 7 there is no horizontal force. Point 8 you have value 5. Okay, actually this is actually not as minus 5. That means this global coordinate should be represented as horizontal 7 and this should be 8, not this one. That's why the value 5 is acting downwards, so there is a minus value. For the AJ, and for the joint displacement we have dj is equal to sjj inverse into aj. So for the value of sjj from this slide and inverse into aj will give you the corresponding joint displacement, and the equation for the member force member 1 is equal to AMI is equal to AMFI plus SMI into RTI into D global I. So the values are just added up. There is no fixed moment as the load is acting exactly at the joint. So this component is not there. No AMF1 is equal to SMI. We know the value into RTI into D global will give you 1.833 and 0, which are the member forces. For the member 2, the value are 2.89 and 0, and for the member 3 values are 1.057 and 0. So this will be the corresponding tension force in the various member. That is we have 1.8330 for the first one, then 2.890, 1.0570. So if you correlate with the initial one, for the one will be the actually the stretching of the member. So for all this action of this 5 kilonewton, you know that all the members will be under tension. The tension value will be the first value, and the horizontal value will be the second value, which is equal to 0. So all the tension values are noted as obtained as 1.8330, 2.890 and 1.0570. Quickly see this problem also. Analyze the given pin jointed truss. A is a constant. So all the length are given, angle is given. Here also we have here you have two member of 5 meter length, and the angles are given to you. So this will be the global degrees of freedom. 1, 2 at the left side, 3, 4 at the tip, and 4, 5, sorry, 5, 6 at the right end. And the connectivity is for the member 1 between node 1 and node 2, and for member 2 it is 2 and 3. It is clear from the picture. And you know the local coordinates for the member 1 and member 2 separately, 1, 2 and 3, 4 on the right side. So always note that it is actually proceeding from 1 to 2, then 2 to 3. So 1 to 2 means 1 will be 1 and 2, 2 will be 2 and 3. For 2 to 3, at 1 and 2 will be on the 2 and 3 and 4 will be on 3. So you should have a correct order as marked here, and you know the individual stiffness matrix element. Sm is equal to this value in general. This is actually in general, and this will be the free degrees of freedom in global coordinate. So there will be already deflection in the 3 and 4 being the supports. This will won't allow any horizontal vertical movement. The support also won't allow any vertical horizontal movement. So out of this global coordinate 1, 2, 3, 4, 5, 6, only the value will be there for 3 and 4. So 1, 2 and 5, 6 can be skipped at the initial stage itself. So we can assemble for the various member. Define for the various member. For the member 1 and 2 support condition restraint. So this 1 and 2 will be completely 0, 1, 0, 2, 0, and the corresponding columns also will be 0. The remaining one will be EA by L 0, 0, 0. This is actually for the 3, 4 where there is some deflection. SM1 is equal to EA into 0.2000. And for the member 2, for the member 2, actually for the member 2, this 1 and 2 is restrained. Okay, so this value will be 0, right? There will be a I'm sorry. There will be value for the 1 and 2 being the tip. This 3 and 4 will be 0. In the previous one, for the member 1, 2 will be 0, and 4, 3, 4 will have some value. For the member 2, 1, 2 will have some value, and the 3, 4 won't have any value being a support. So hence the 1, 2 will be there. All the 3, 4 will be getting cancelled. 3, 4. Corresponding rows also for 3, 4 will be cancelled. The EA by L 0, 0, 0 will be the corresponding one, which is SM2. And also the rotation matrix will be theta is 30 degree. So it's actually correctly oriented as in our case there will be a angle will be like this, theta. For the member 1, theta is equal to 30 degree, and for the member 2, theta is equal to minus 30 degree. Because actually this is anti-clockwise, which is positive, and for this one it is clockwise from the horizontal axis, theta. To get the RT2, RT1, then the member stiffness matrix in global coordinate, we have to convert it into the member stiffness matrix. So SM S1 is equal to RT1 transpose into SM1 and RT1 for the member 1 to get the value in global degrees of freedom 3, 4. And also SM2 will be equal to this value. This also will be in the 3, 4 for the global coordinate. Then you can assemble it, add for the both member ends to get the total system structure matrix. Sorry, stiffness matrix. This is a reduced global stiffness matrix since the restraint degrees of freedom were not considered, hence the boundary conditions are automatically incorporated. We have already cancelled or neglected the support displacements. AJ is equal to 50. So here the load will be at this point horizontal. We have this coordinate, no? Like the 3 and 4 will be horizontal and vertical. 3 will have some value 5 and 4 will be 0. So it will be correctly the 50. And the joint displacement dj is equal to sjj inverse into aj is equal to 1 by ea into 0.30, 0.1 inverse into 50 will give you 1 by ea into 16.670. So this will be the joint displacement, and this 16.67 by ea will be the deflection at the point at the top point in this direction, because the load is acting in the horizontal direction and there is no vertical displacement. And the member forces, every member will be having forces with the application of this force. So the member one, individually we have to find for the different members. For the member one, we have AM1 is equal to AMF1 plus SM1 into RTA into V global. We know the AM will be 0, no fixed moment. Substituting 2.89 and 0. So 2.89 will be in the direction of 1. So in the direction of 1 means this direction. This will be 2.89 and this will be 0. So that will be under tension. Hence the value positive 2.89, and for the member 2 it will be minus 2.89. So upon the action of essentially cross check, upon the action of the cyclonewton, this member will get stretched and this member will get compressed. So this is actually positive 2.89 and this will be minus 2.89. Stop for today.